The universe was a place of extraordinary, catastrophic violence, whose specific scale made every human conception of an explosion, a bomb, a building collapse, a volcanic eruption seem not merely small but cosmologically invisible. Here's every type of cosmic explosion, explained in full. Let's break this down. Gamma ray burst. Gamma ray bursts were the most energetic individual events in the observable universe, the single most powerful class of explosions that astronomers had detected since the first confirmed observation in 1967, when the Vela satellites, deployed to monitor for violations of the Nuclear Test Ban Treaty, detected gamma radiation from space, whose specific signature was entirely unlike any nuclear weapon detonation, and was ultimately identified as the first recorded gamma ray burst from a cosmological source. A gamma ray burst was the impulsive release of supernova-level energy, but instead of blasting away in all directions, the burst was concentrated into a pair of tightly focused beams, the collimation of the energy into two narrow jets rather than a spherical explosion being the specific property that made gamma ray bursts so extraordinarily luminous to a distant observer aligned with the jet. Because the same energy that a supernova spread across the full sky was concentrated by the jets into a beam narrow enough to be detected across cosmological distances. Gamma ray bursts were so intense they could be seen from incredible distances. One, called GRB 8031b, erupted 7.5 billion light-years from Earth and yet was briefly visible to the naked eye, its gamma ray emission being so energetic that even across half the observable universe's diameter, it was detectable with the dark-adapted human eye for approximately 30 seconds, making it the most distant object ever visible to unaided human vision. Astronomers divided gamma ray bursts into two fundamental classes based on their duration: short bursts lasting less than 2 seconds, and long bursts lasting from 2 seconds to several minutes or occasionally hours. Astronomers now associated short bursts with the collision of either two neutron stars or a neutron star and a black hole, resulting in a black hole and a short-lived explosion. The merger of two neutron stars being the most energetically extreme collision of compact objects available in the universe, and producing a burst that released more energy in less than 2 seconds than the sun would emit across its entire 10 billion year life. Long bursts were linked to the explosive deaths of massive stars. When a high-mass star ran out of nuclear fuel, its core collapsed and then rebounded, driving a shockwave outward through the star. And in both classes, the newly born black hole beamed jets in opposite directions at velocities approaching the speed of light. The jets, made of particles, accelerated to near the speed of light, pierced through, and eventually interacted with the surrounding material, emitting gamma rays when they did. The afterglow that followed the initial burst continuing to radiate at lower energies for hours, days, and in some cases months after the burst itself. Closer than approximately 6,000 light-years, a gamma ray burst aligned with Earth could strip the ozone layer from one entire hemisphere of the planet and produce mass sterilization of the exposed surface. And some scientists had proposed that gamma ray bursts might explain certain mass extinction events in Earth's geological record, whose cause remained unclear. Supernova. Supernovae were the most common of the universe's truly catastrophic explosions, the deaths of stars that released approximately 10 to the power of 44 joules of energy, a quantity so large that writing it out in standard numerical form required 44 zeros, and that exceeded the total energy the sun had radiated across its entire life by a factor of approximately 10,000. For a few days, a supernova emitted as much energy as a whole galaxy. The specific comparison communicating the scale of the event, the death of a single star briefly outshining the combined light of hundreds of billions of stars in its host galaxy, the luminosity spike visible across billions of light-years as a transient brightening of what had been a previously unremarkable point of light. There were two fundamentally different types of supernovae: thermonuclear explosions, which occurred when a white dwarf was pushed above its maximum mass of 1.4 solar masses, the Chandrasekhar limit, leading to the complete disruption of the star in what was called a type Ia supernova, and core collapse supernovae, which took place when the core of a massive star had exhausted all of its nuclear fuel, the core collapsing to leave a compact remnant of a neutron star, or in some cases a black hole. The thermonuclear supernova, type Ia, was the explosion that had revealed the accelerating expansion of the universe in 1998, the specific consistency of the peak luminosity of Type Ia events across cosmic distances, making them reliable standard candles for measuring the expansion history, and the discovery that the most distant Type Ia supernovae were fainter than expected, communicated that the universe's expansion had been accelerating rather than decelerating, requiring the existence of dark energy as the repulsive cosmic component driving the acceleration. The core collapse supernova was the more common of the two. Massive stars above approximately 8 solar masses ended their lives this way. And the shockwave produced by the core's bounce enriched the surrounding interstellar medium with oxygen, carbon, neon, magnesium, silicon, and all elements up to iron that had been synthesized in the star's core during its lifetime, distributing the products of billions of years of stellar nuclear burning into the galaxy for incorporation into the next generation of stars and planetary systems. SN 1987A, the closest supernova observed in the telescope era, located in the Large Magellanic Cloud approximately 168,000 light-years from Earth and detected on February 23, 1987, produced the first direct detection of neutrinos from a supernova, 11 neutrinos arriving at the Kamiokande detector in Japan within a 13-second burst, confirming the theoretical model that the vast majority of the supernova's energy was carried away by neutrinos rather than light. Kilonova. A kilonova was the cosmic explosion produced by the merger of two neutron stars, or a neutron star and a black hole. One of the most energetically extreme collision events available in the universe, and the astrophysical process responsible for the synthesis of approximately half of all the elements heavier than iron in the observable universe, including the gold, silver, and platinum whose presence in Earth's rocks and human technology trace back to the mergers of stellar remnants billions of years ago. Short gamma-ray bursts were sometimes followed by kilonovae, light produced by the radioactive decay of chemical elements that decay, generating even heavier elements like gold, silver, and platinum. The specific mechanism of kilonova nucleosynthesis was the rapid neutron capture process, the R process, in which the extreme neutron flux produced in a neutron star merger allowed atomic nuclei to capture neutrons at a rate far faster than they could decay, building up nuclei with far more neutrons than stability permitted in normal terrestrial conditions, and then decaying through a series of beta decays to produce the stable heavy isotopes that populated the upper end of the periodic table. The first confirmed kilonova was GW17U8I17, detected on August 17, 2017, when the LIGO gravitational wave detectors first heard the merger of two neutron stars 130 million light-years away, followed within approximately 1.7 seconds by a short gamma-ray burst detected by the Fermi and Integral space telescopes, and then over the following days and weeks by the kilonova's optical and infrared emission detected by dozens of telescopes worldwide. The gravitational wave detection and its electromagnetic counterpart together represented the most scientifically productive single astronomical observation in history, simultaneously confirming the connection between neutron star mergers and short gamma-ray bursts, confirming the R process as the site of heavy element nucleosynthesis, providing a new way to measure the Hubble constant, and demonstrating that gravitational wave astronomy could be conducted in coordination with traditional electromagnetic observatories. Nova. A nova was a thermonuclear explosion on the surface of a white dwarf star in a binary system. A significantly less energetic event than a supernova, because it destroyed only the accreted surface layer rather than the entire star, the white dwarf surviving the explosion and continuing to accrete material from its companion for another nova eruption thousands to hundreds of thousands of years later. In a nova system, a white dwarf accreted hydrogen from a companion star, the same process that in a Type Ia supernova was taken to the extreme of the Chandrasekhar limit, but in a nova stopping short of that limit and instead producing a thermonuclear runaway only in the accreted hydrogen shell on the white dwarf's surface. The specific sequence was hydrogen from the companion accumulated on the white dwarf's surface. The bottom of the accumulated layer was compressed and heated by the weight of the material above it. The temperature eventually reached the threshold for thermonuclear ignition of hydrogen. The runaway fusion spread across the surface in a detonation that ejected the accreted layer at velocities of hundreds to thousands of kilometers per second, while the white dwarf itself survived intact. RS Ophiuchi, a recurring nova that had erupted in 1898, 1933, 1958, 1985, 2006, and 2021, was the most studied recurrent nova system, its regular eruption cycle demonstrating directly that the white dwarf survived each nova event and continued accreting toward the next one. The 2021 eruption of RS Ophiuchi was the first nova bright enough to be visible to the naked eye since GK Persei in 1901, reaching apparent magnitude 4.5 and being visible as a new star to observers in dark sky locations, reproducing for a modern generation of observers the experience that had led ancient astronomers to coin the Latin term nova stella, new star, for these sudden stellar brightening events that had always appeared without any prior warning in positions in the sky where no bright star had previously been visible. Magnetar giant flare. A Magnetar giant flare was the most energetically extreme event that a single star could produce without destroying itself. A sudden release of electromagnetic energy from the surface and magnetosphere of a magnetar, the most strongly magnetized class of neutron star known, whose magnetic field strengths of 10 to the power of 14 to 10 to the power of 15 Gauss exceeded Earth's magnetic field by approximately 10 billion times, and stored enough magnetic energy to produce a burst lasting only a fraction of a second that released more energy than the sun would emit in tens of thousands of years. A magnetar was a young neutron star with an exceptionally strong magnetic field. The star's rapid rotation and internal convection during the neutron star's formation having amplified the magnetic field through a dynamo process to levels that had no equivalent elsewhere in the observable universe. The December 27, 2004 Magnetar giant flare from the Magnetar ASGR 180620, located approximately 50,000 light-years from Earth in the constellation Sagittarius, was the most energetic event ever recorded within the Milky Way, its initial half-second spike releasing more energy than the sun would emit in 250,000 years, and despite being 50,000 light-years away, it was powerful enough to compress Earth's ionosphere and briefly affect the upper layers of the atmosphere, the most dramatic direct effect of any astronomical event on Earth's environment since a nearby supernova deposited radioactive iron-60 in oceanic sediments approximately 2.6 million years ago. On November 15, 2023, ESA's satellite Integral spotted a sudden explosion from a rare object. For only a tenth of a second, a short burst of energetic gamma rays appeared in the sky from what was subsequently determined to be a Magnetar giant flare in a nearby galaxy, the first extragalactic Magnetar giant flare confirmed by multiple lines of observational evidence, communicating that the most extreme magnetic neutron stars were producing events visible across millions of light years. Tidal disruption event. A tidal disruption event was the cosmic explosion, or more precisely, the extended energetic eruption, produced when a star wandered too close to a supermassive black hole and was torn apart by the tidal forces of the black hole's immense gravity, the shredded stellar material forming an accretion disk around the black hole and producing a luminous flare of radiation as approximately half the star's mass fell inward and was converted to energy with extraordinary efficiency, while the other half was flung outward at velocities sufficient to escape the black hole's gravity. Tidal disruption events created about the same total amount of energy as regular supernovae. The comparison communicating both the scale of the event and its significant difference from a supernova, a TDE being not an explosion in the conventional sense, but an extended period of extraordinarily luminous accretion lasting weeks to months as the stellar debris gradually settled onto the black hole. First observed in the 1990s, TDEs were produced when a star ventured too close to a supermassive black hole in the core of a distant galaxy, and was torn apart by the gravity difference between the near side and far side of the star. The tidal force being the gradient of gravity, which became destructive at a distance from the black hole called the tidal disruption radius, where the black hole's tidal force exceeded the star's self-gravity. As astronomers discovered more TDEs, they identified a subset called jetted TDEs, events in which the disruption produced a relativistic jet aligned toward Earth, boosting the apparent luminosity by a large factor and making the event detectable at distances that ordinary TDEs could not reach. The April 2025 detection by the Einstein probe of an unusual event designated EP244048A represented the kind of ambiguous event at the boundary between gamma-ray burst and jetted tidal disruption event that was forcing astronomers to refine the classification system as new observational capabilities revealed more extreme and more unusual members of the cosmic explosion population. Hypernova. A hypernova was the most energetic subset of core collapse supernova, stellar explosions whose total energy release exceeded the standard core collapse energy by factors of 10 to 100, requiring physical mechanisms beyond the standard neutron star formation process to explain the extraordinary energy output, and whose association with some of the universe's most energetic long-duration gamma-ray bursts made them the most scientifically significant stellar explosions in the universe after the gamma-ray bursts themselves. Broadline Type Eq supernovae that had very high ejecta velocities and broad spectral features were often exceptionally energetic, frequently associated with long gamma-ray bursts, the category of stripped core collapse supernovae, whose spectral broadening communicated ejecta velocities of 20,000 to 30,000 kilometers per second, rather than the typical 10,000 kilometers per second of standard supernovae, with SN 1998 Baua linked to gamma-ray burst, 9800425 being the archetype. The hypernova of SN 1990 released approximately 10 times more kinetic energy than a standard core collapse supernova and synthesized approximately 10 times more radioactive nickel-56, the higher nickel production being the primary mechanism for the hypernova's greater peak luminosity, the radioactive decay of nickel-56 to cobalt-56, and then to iron-56 being the energy source that powered the supernova's optical luminosity for weeks after the explosion. The collapsor model, the theoretical framework for how hypernovae and their associated gamma-ray bursts were produced, described the collapse of a rapidly rotating massive star directly into a black hole with an accretion disk whose magnetic processes launched relativistic jets through the stellar envelope at velocities close to the speed of light, the same jets that produced the gamma-ray burst being surrounded by the wider cocoon of slower-moving shocked material that produced the hypernova's broader supernova-like emission. The rotational energy extracted from the collapsing core and deposited into the jets was the additional energy source that distinguished a hypernova from a standard core collapse supernova, and the specific requirement for rapid rotation in the progenitor star communicated that hypernova were preferentially produced by stars that had retained their angular momentum during their stellar evolution, most plausibly through the binary mass transfer interactions that had stripped the hydrogen envelope while preserving the core's spin.